For thousands of years, petroleum has seeped through the Earth's crust in many places, where evaporation and oxidation gradually change it to sticky bitumen or pitch. Natural gas and mineral waters frequently bubble to the surface with the oil and give only a hint of possible underground supplies. Legend and authentic record agree that men have used petroleum in some form since ancient times. Genesis contains this account. And God said unto Noah, Make thee an ark of gopher wood. Room shalt thou make in the ark, and shalt pitch it within and without with pitch. Early settlers in North America found that Indians had various uses for petroleum, obtained by skimming pools where it had seeped. They put the oil in a blanket, through which most of the water was strained, so that a small quantity of petroleum remained. The Indians employed this crude oil for medicines, liniment, and hairdressing, a mere suggestion of the many cosmetics and medicines that would be devised later. Before long, peddlers built up an active business selling this liquid obtained from brine wells and seepages, and commonly termed rock oil. The root words of petroleum are, in fact, petra, meaning rock, and oleum, meaning oil. Wonderful medicinal virtues were claimed for the oil, which had a wide sale, especially in country districts. In May 1859, Colonel Edwin L. Drake began to drill a well near Titusville, Pennsylvania, after many long, discouraging delays. A few years earlier, experimenters had obtained from rock oil a liquid similar to coal oil, which was distilled from coal and used in lamps as fuel. By drilling this well, Drake and his financial backers hoped to find an adequate supply of crude oil without having to skim it from pools of water or extract it from brine wells. To prevent the flow of surface water into the hole, Colonel Drake and his driller, Uncle Billy Smith, devised a method of driving a pipe into the hole as drilling progressed. This drive pipe was the forerunner of the steel casing used in all modern oil and gas wells. When the bit struck hard rock, special tools patterned after those used by brine well borers in exploring for salt were hooked to a walking beam, which moved them up and down in the hole. A small steam engine at the rear of the rig supplied power to operate the walking beam. Drillers at that time believed that it was necessary to turn the tools in every direction to assure a round hole. Uncle Billy and his son were drilling at a depth of 69 feet on the afternoon of August 27, 1859, when oil suddenly filled the pipe to the level of the surface of the ground. After pulling the tools, they bailed out several buckets of oil. The well did not flow, and its production was not large, probably about 25 barrels a day, according to various estimates. But nearby mill hands who rushed to the site in amazement could hardly believe the spectacle of oil coming from a well like water. The event had historical significance because the drilling of this shallow well introduced new factors throughout the world with respect to its supply of fuels and lubricants. A pitcher pump was rigged up and put to work at this pioneer well. When Colonel Drake arrived, he had dressed for the great occasion in his silk topper and Prince Albert. Meanwhile, several barrels had been filled with oil, Although it was worth about $40 a barrel, Drake never became wealthy from his achievement. Nevertheless, he started the first oil boom. Enterprising pioneer oilmen who could not obtain steam drilling equipment rigged up ingenious but primitive mechanical devices known as spring poles to drill their wells. Of course, drilling with this improvised cantilever was painfully slow, depending upon the spring of a sapling to bounce the tools in the well. The Chinese used this principle centuries ago in drilling brine wells for salt. These early oil producers also faced difficulties in moving their oil to market. Teamsters demanded $2.50 to $5 per barrel for 8 to 20-mile hauls. Barrel makers, too, enjoyed an era of prosperity. In the spring, freshets carried barrel-laden barges down Oil Creek to the Allegheny River, where their cargoes were transferred to riverboats. The petroleum industry progressed. Oil field development moved steadily south and west from tree-covered Pennsylvania hills. At one time, fantastic forests of closely spaced wooden derricks sprang up. Then, as the search for new fields grew more urgent, the industry reached the prairies. Wells were spaced in long, orderly array. Even cities were invaded with modern steel derricks, which thrust their crown blocks high above the surrounding buildings. Drilling extended even beyond the coastline of this great continent. In a little over 85 years, this sweeping movement left behind more than 1 million wells. Some are historic, many others are forgotten, yet each has had a part in the evolution of the vast oil industry. But derricks alone do not tell the full story. In the search for oil, geologists at one time depended entirely upon the study and mapping of surface indications to guide them to petroleum deposits. Today they have geophysics to help them. One method used widely to determine favorable underground conditions is known as reflection shooting. This type of underground prospecting requires shot holes drilled rapidly at predetermined locations to shallow depths with modern, lightweight rotary equipment. Each hole is loaded with a charge of dynamite, placed at the bottom by jointed tamping rods. When the charge is exploded, the blast creates an artificial earth tremor. A short distance away, the crew of a mobile laboratory strings sensitive electric ears, called geophones, placed to pick up the reflected earth waves. An insulated circuit connects them to apparatus in a truck. The truck is equipped with precise electrical instruments that record the earth waves or seismic waves originating with the explosion, which are reflected back to the surface from the denser beds of buried rocks. When all is in readiness, a charge is fired, and each geophone, because of its known position with respect to the shot, picks up a different reflected wave which is recorded photographically. The operator develops the photographic wave chart immediately. From a large number of different recordings, the depth and shape of deeply buried beds of rock are determined. This modern method of prospecting is also used offshore to find structures along our coasts and in the Gulf of Mexico. A large fleet of power launches carries the bulky geophysical equipment. Geophones of special design are used underwater. The crews often work several miles offshore. The geophones and explosive are lowered to sea bottom. Their respective positions are known. The charge is set off and recordings similar to those on land are made. One spectacular aid in the search for oil is the marsh buggy. Grotesque mechanical amphibians like these make it possible to explore for petroleum by geophysical methods in places otherwise inaccessible. The lowland country of the bayous and the Gulf Coast marshes present barriers almost impassable for survey parties equipped only with ordinary transportation. After geologists have pointed out where a productive petroleum deposit may be found, a derrick, often as high as a 15-story office building is built. It is equipped with machinery for drilling the well and for lowering the drilling tools into the ground and for raising them out of the hole at frequent intervals. Many wells exceed 2 miles in depth, and as much as 3 miles has been reached. An efficient power plant is essential for drilling a well and lining it with steel pipe. The deep formations are reached because of the expertness of the driller and his crew, aided by information gained from instruments on the control board. When a bit becomes dull, the crew must pull the drill pipe, which consists of long sections screwed together. To raise the bit to the surface, the drill pipe is unscrewed in stands. Here is a view of the operation from below. Hoisting cables raise the stands of pipe, gripping them in large clamps or elevators, which are unlatched by the derrick man on the platform high above. At last the dull drill bit reaches the surface, where it is replaced with a sharp one. After the sharp bit has been attached, it is lowered into the hole, and the stands of drill pipe are screwed together again. Driller and crew may require several hours of closely coordinated work for making a round trip to change a bit before drilling is resumed. In all rotary drilling, special mud fluid is pumped to the bottom of the hole through the drill pipe under pressure, forced out through the ports in the bit, and thence returned to the surface. This action flushes the cuttings, cools the bit, prevents caving, and otherwise protects the hole. Clay no longer is dug in nearby sumps. In modern practice, the drilling fluid is a mixture carefully compounded by a chemical engineer to conform with changing conditions as drilling progresses and to prevent blowouts. The chemically treated mud is mixed in tanks, which can be moved from one rig site to another. A vibrating screen or shaker removes cuttings as drilled, but permits the drilling fluid to pass on to the mud tanks, where it is cooled and later treated with chemicals for recirculation. For drilling in bayous and offshore along the Gulf Coast, the derrick and all its equipment are mounted on barges resting on shallow bottom and lashed to piling. The unit is self-contained and even includes living quarters for the crew. Drilling technique is much the same as on land. Electrical logging invented by French engineers reveals many facts concerning the nature of the well formations. Like probes, electrodes are lowered into the hole, and their distance from the surface is frequently measured. The effect of an electrical current sent through the cable to one electrode is measured by the intricate instruments in the cab. These measurements indicate where oil, gas, and water may occur because of the varying electrical resistance of the underground formations. The data are recorded photographically upon such charts as this. Comparison of a log with those of adjacent wells helps geologists to find the best pay formation in the well. Tons of cement mixed with water are pumped down the inside of the steel casing and into the space between the pipe and the walls of the hole. The ring of hardened cement excludes underground waters, protects the casing, and prevents damage to oil and gas zones. Chemical engineering has made possible large-scale treatment of wells with liquid chemicals. 5,000 gallons of chemicals were injected into this well. Acid frequently is used to open passages in limestone formations. In other wells, chemicals form a solid plug to prevent water migration or to seal open strata. These sharp-nosed steel bullets are shot from a gun perforator through the walls of steel casing far below the surface to make openings for oil and gas to flow into a well. Shells that look something like hand grenades eject the bullets with great force from the sides of the gun perforator after it is lowered to the desired depth. The muzzle velocity of the bullets is great. despite the shortness of the gun bore. Engineers have also devised core barrels that cut samples of the rocks penetrated by the bit and bring them to the surface. The arrival of a core from the bottom of the hole is a tense moment. By tasting and smelling this sample, an experienced person can tell much about the oil-producing possibilities of the formation. The final word, however, must be said by the analyst, who determines with exactness what taste and smell can only suggest. He tests the cores carefully in a portable field laboratory to estimate the oil content and other characteristics of the prospective oil zone. Some oil companies use a central laboratory to check the results of field laboratory tests. Here, more elaborate and precise equipment is available, and core samples from many wells can be examined in greater detail. The volume of the small openings in rocks that may contain oil is known as the porosity and is a highly variable characteristic. It is an important factor in estimating the quantity of oil that a producing formation may contain. Permeability tests determine the rate at which fluids will flow through the porous rocks. Such information is important in appraising production rates and deciding on treatment and operation of a well. But the principal interest to producers is the quantity of oil in the core sample. Specimens are heated in retorts, the oil they contain is driven off as vapor, then condensed and measured. From the results, the number of barrels of oil per acre can be computed. In another laboratory procedure, the crude oil is washed out of the porous rock samples in glass extractors with a petroleum solvent, separated by distillation and measured. Not only in the laboratory, but in the oil fields, modern science has developed many services that make the control of wells more efficient, and by means of which information is obtained concerning conditions far beneath the surface. So-called bottom hole recording instruments are lowered on strong wire lines to obtain temperature and pressure readings at different known depths. Encased in steel shells, the carefully machined working parts must perform with clock-like precision. Such readings in wells have become routine procedure in most oil fields. Bomb-like devices obtain bottom hole samples of natural mixtures of oil and gas under pressure from wells. Transferred to other high-pressure containers, the hydrocarbon material is analyzed by research engineers. Such scientific control conserves crude oil, formerly lost. Now the liquid from the wells is piped to vapor-tight field tanks and still contains most of its volatile gasoline fractions. Natural gas produced with crude oil, such as that coming from vapor-tight tanks and oil field separators, contains valuable gasoline and other liquids that may be extracted and used for later blending into high-quality gasoline. The gas is compressed, then cooled to liquefy the gasoline fractions. Or the gas is bubbled through a special oil, held on a series of trays arranged in tall towers, which absorbs the gasoline for later recovery by distillation. The dry tail gas is pumped to market through pipelines or injected underground by these compressors into producing horizons, where it will help to force more oil to the surface. Many deep formations contain liquefiable petroleum hydrocarbons, called condensates, that do not become liquid until the pressure on them is reduced. The liquids are extracted in cycling plants. To prevent condensation and loss of liquids in the reservoir rocks by maintaining the natural pressure, large compressors pump the remaining dry gas through carefully selected wells back to the reservoir whence it came. Most of our crude oil comes from pumped wells. Some units resemble mechanical animals. This central unit suggests a giant straddlebug with its long steel pull rods reaching out to animate the pumps at widely separate wells. Oil and oil products, from their sources of supply to their points of use, today travel through arteries of steel. Pipelines laid in the ground bring petroleum and natural gas from wells and their liquid products from plants to terminals and refineries. Picks and shovels are still essential tools of the pipeline gangs, but most trenching is now done by machines that take great bites out of the soil and pile an even row of dirt alongside for easy backfilling. The modern method of stringing pipe with portable booms and hoists is a great improvement over old-time manual labor. Progress in welding has completely changed the technique of building pipelines. Formerly, the joints of pipe were screwed together, but now these long, seamless tubes are welded either by a gas flame torch or an electric arc. Before pipe is covered in the ditch, it must be cleaned thoroughly and protected against pitting and the corrosive action of chemicals in the soil. Here again, hand methods have yielded to modern mechanical ingenuity. In one operation, the pipe is cleaned with revolving wire brushes and covered with a specially compounded bituminous coating. Because this material is applied hot, pipeline men call such coating hot stuff. Wrapping follows the hot application. Another machine applies a smooth spiral covering which acts as a further protection against corrosion and stray electrical currents that cause pitting. Thus, the life and serviceability of the lines are prolonged. In pipeline construction, streams and rivers must be crossed, calling for special engineering, ingenuity, and mechanical equipment. The pipe, as finished, is lowered to the bottom of the stream and securely anchored. Often amid beautiful surroundings, rugged utility makes itself felt as the heart of the crude oil pipeline throbs with the pumping of oil from one station to the next. These mighty steam-driven reciprocating pumps, combined with others, can handle 200,000 barrels of crude oil a day. The pumping of gasoline through pipelines presented many technical problems, and the first line of this type was hailed as an engineering triumph. This station is powered by diesel engines installed for safety behind the firewall through which extend the shafts that turn the centrifugal pumps. The operator takes frequent careful measurements of the pressure, quantity, and characteristics of the products being pumped. Some gasoline pumping stations are electrically operated. 700 horsepower turns the rotors of this pump as rapidly as an airplane propeller, and almost 30,000 barrels of gasoline can be pumped in a day. To meet ever-growing needs, the United States has an underground network of more than 100,000 miles of crude oil and gasoline pipelines joined in sections. Branches of the main truck systems extend to virtually all parts of the country and interconnect oil fields, land and marine terminals, and refineries. Petroleum refineries make hundreds of different petroleum products. These modern plants cover vast areas with complicated equipment and many types of storage facilities. All this has evolved through scientific research guided by experiments in laboratories and pilot plants. Early refiners depended largely on rule-of-thumb methods. They distilled crude oil in vertical cheese box stills. For many years, kerosene was almost the only product, and gasoline was wasted by burning or discharging into creeks and rivers. About 1900, the early automobiles began to create a demand for the gasoline that hitherto had been a problem for refiners because it had few uses and was dangerous even to throw away. To fill increasing demands for more and better gasoline, refiners developed shell stills, operated at low pressure and temperature in series or as units. Pipe stills then supplanted the shell stills at many refineries, resulting in safer operating conditions and improved products. By a simple distillation process, A pipe still unit separates crude oil into such raw products as gasoline, kerosene, gas oil, lubricating oil stocks, and heavy fuel oils. A real advance in refining technology followed adoption of cracking processes on a commercial basis. In cracking stills, the larger and more complex molecules of the heavier oils are broken down or cracked by heat and pressure. Huge combination units were developed to handle both distilling and cracking, oil refining operations that formerly required separate steps. Such units are now processing many thousands of barrels of crude oil daily. Control instruments of almost human ingenuity keep constant watch over the manufacturing processes throughout the refinery. In units called polymerization plants, some gaseous hydrocarbons are brought in contact with a solid catalyst under controlled pressure and temperature to form a liquid which is modified by a reaction with hydrogen to produce one of the main blending stocks for aviation gasoline. Catalysts, agents that promote a reaction without taking part in it, also are used in types of cracking units recently developed for converting heavy oil into gasoline. Cat crackers, as they are called, make a superior grade of distillate which is blended with other materials to obtain high-quality motor fuel. Some of the gases formed in catalytic cracking are used in manufacturing synthetic rubber. In this plant, highly reactive gases from cracking processes are absorbed by sulfuric acid and refined into a liquid called alkylate, a blending stock for aviation gasoline. In this new alkylation plant, hydrofluoric acid has replaced sulfuric acid as the absorbent in the manufacture of alkylate. Gases that have not been absorbed in the first contact with the acid are separated from the alkylate in these towers and returned to the plant cycle for further processing. A recent outstanding development in the petroleum industry has been the conversion of refinery gases into butadiene, used in the manufacture of synthetic rubber. Feedstock for butadiene manufacture is stored in spherical tanks under pressure to keep it liquid. Similar tanks provide storage for liquid butadiene before it is pumped to the rubber plant. Petroleum lubricants, essential in a mechanized world, are an important product of petroleum refining. In 1845, textile manufacturers mixed petroleum from seepages with sperm oil to lubricate cotton mill spindles. Today, hundreds of lubricants and greases serve modern mechanical needs. Lubricating oils are improved by solvent refining. In this plant, wax is removed. The refined wax is melted and run into specially devised molds where it is shaped into cakes of uniform size and weight. After cooling, the solid cakes are separated from the molds, removed and packed for shipment to all parts of the world. Research laboratories are important factors in the evolution of petroleum refining. Scientists are constantly studying different oils and processes to improve the quality of products and to devise new and better methods. Here, test equipment, including automobile engines and dynamometers, determines the characteristics and quality of gasoline, lubricants, and other products. The object of all this huge investment and the many operations from exploration to manufactured products is to serve the varying demands for gasoline, fuel oil, lubricants, and other commodities that were unobtainable a few decades ago with simple distillation in low-capacity shell stills. Moreover, a vast and efficient transportation and distribution system had to be created to handle petroleum products. Finished products are distributed from refineries by rail, pipeline, truck, and water. Tank cars serve some markets not reached by pipelines, and many thousands of barrels a day are handled in this way. Giant tankers carry huge cargoes of petroleum in many forms over the 7 seas. Majestically, the loaded tanker clears the harbor on its voyage, perhaps to domestic or to foreign ports, or perhaps to refuel ships at sea. Trained crews face fair weather or heavy seas that put the decks awash, confidently holding the sturdy vessel to her course. Tank trucks, the final link in the system of distribution, deliver gasoline and other fuels to industrial plants, farms, homes, and retail service stations. Thus we see the processes of growth, evolved from small beginnings almost within the memory of one man. This great petroleum industry in all its branches, exploration, drilling, production, refining, transportation, and marketing, now rests upon a solid foundation of science, technology, and ingenuity. All these costly operations are back of the petroleum fuels that furnish power to automobiles and provide the oils and greases for lubricating. The diesel-powered units that drive our streamlined trains. The steam or diesel engines that propel great ocean liners. The conquest of the air, and myriad other contributions to our complex modern life. Where petroleum will be found and what further evolution will take place, time alone will reveal.